All right, so the first thing I want to talk about is a question that is not necessarily 100% like what we did yesterday, but it kind of maybe opens your eyes to the purpose of what we were doing yesterday. So if I can get this thing to disappear, there we go. So and basically what's going to happen here, guys, is I want to take a algebraic approach to a question and then slightly alter it to see, actually, let's do it this way. Let's phrase it as a numerical approach to a question, then the exact same question algebraically, and then the exact same question trigonometrically, okay? And see the parallelisms that are created when we're doing this. And it might open your eyes to why we were doing what we did yesterday by rewriting a expression, a trigonometric ratio, in terms of another trigonometric ratio. So, first thing I want to talk about is something like this. I think the last class we did something like, let's say I take 2 plus 1/2 all over 2. All right, this is purely numerical. I'm just asking you, can you simplify that? Okay. So what would I need to do? Let's go step by step. What would I need to create up here to add those together? Common denominator, right? So I rewrite that as 4/2 plus 1/2 all over 2, correct? So just be, and I heard somebody say it's 5/4 right off the bat. So yes, absolutely, okay? Which is great that you can do that. But I want to be deliberate with the steps here, because when I change it to algebraic with, instead of 2, but x's, we're going to want to go through this process that we're doing here. So I get 5 over 2 over 2. And then that turns into 5 over 2, because this 2 here becomes 2 over 1, right? So I multiply by that reciprocal, and it turns into 5/4. Everybody agree with that? Okay. Let's do it this way. Let's say that instead of 2 plus 1/2 over x, for that one real number 2, let's see if it works, or that we can do this for all real numbers like 2. So let's say we write this as x plus 1 over x all over x. And hopefully the idea of college algebra and algebra 2 is helping us develop the understanding that what we did here in 7th grade, 8th grade, 9th grade math is the exact same thing we do down here, right? Okay. The variable just stands in for all those different things that 2 could have been. So again, same process, common denominator, right? What's common denominator going to be here? X. So I'm going to rewrite this top as x over x plus 1 over x. Bottom stays x. Okay. Now, doesn't this, I made a mistake, doesn't have to be x squared? Okay. So I multiplied this by x over x. Okay. So that turns into x squared plus 1 all over x divided by x, right? Well, at that stage right there, didn't we put this over 1? Multiply by its reciprocal, correct? Now doing that, we get x squared plus 1, okay, all over, now x times x, just like up here, is 2 times 2, so it's a perfect square of 4, right? Well, x times x gives me the perfect square, x squared. Now, how do we see if those two things are actually correct, or that the red one is correct? Plug 2 in, right? Plug 2 in, I get 2 squared plus 1 over 2 squared. Is that 5/4? Absolutely. Okay. Now, let's take it one step further and go into kind of the trigonometric realm of things. Let's say that I want to rewrite this as tangent of A plus 1 over tangent of A divided then by tangent of A. Is that in the exact same form as the red one? Yeah. And guess what tangent of A represents, guys? Just a number, okay? I don't know what that number is, okay, because I don't know what A is, but run it through the tangent function, and you get an output. So it could be eventually 2. It might be 2, okay? It might not be. It might be, 1.3457. It might be radical 3 over 3. I don't know, okay? But we should be able to go through the exact same approaches. So now, and this I think is going to open your eyes to maybe the purpose of what we did yesterday. If I'm going to do this work here, just like I did in these previous two, I'm going to come up with a common denominator, right? What's that common denominator going to be for that top fraction? If I look at this top fraction here, what's the common denominator going to be? Tangent A. So I'm going to multiply this one by tangent A over tangent A, so it gives me tangent squared A over tangent A plus 1 over tangent A, all divided by that tangent A, right? Sometimes I forget to put my parentheses here. Can I rewrite that then, just being kind of deliberate, as tangent squared A plus 1 all over tangent A over tangent A? Does that make sense to everybody? Okay, so right now, this line here is kind of analogous to there. I multiply by this reciprocal, right? Okay, the reciprocal of that would be 1 over tangent A. So what's that give me? Tangent squared A plus 1 all over tangent squared A. Now, that matches directly to that or to that, right? But we've learned something else prior that's going to allow us to rewrite tangent squared A plus 1 in terms of something else. What is tangent squared A plus 1 the same as? Anybody remember? Say again? Secant squared. Okay? Remember this trigonometric identity here, and this is what I was talking about the other day. If you didn't memorize this, you know that one exists. You know, sine squared plus cosine squared plus 1 or equals 1 exists. If I go through and divide everything by cosine, I get this, right? Okay, so I can generate that. Now, the reason I maybe want to do that is because I see the tangent squared plus 1. That is something that I should commit to memory. That when I see tangent squared plus 1, that is something important. Okay? So I'm going to come down. Just a second, Amy. I'm going to come down and rewrite this tangent squared A plus 1 as secant squared A. Does that make sense? Okay. Now, what's tangent squared A the same as? Sine squared over cosine squared. Now, the reason I do that is because I recognize that secant squared is actually what? 1 over cosine squared. I'm running out of room here. But I had 1 over cosine squared divided by sine squared A over cosine squared A. When I take that bottom fraction, come up with its reciprocal, let me do this work. Let me draw this work over here where I got some more room. I would have 1 over cosine squared A times cosine squared A over sine squared A. Is everyone okay with that? We'll see how the cosines. Cancel. Leaves me 1 over sine squared A, which is equivalent to cosecant squared A. Did that thing become much simpler than that thing? Does that kind of make sense? Okay? So that's kind of the purpose of why we do this. We want to take something that's complex looking, has multiple tangents and multiple evaluations for A. Let's think about it. And for some reason, maybe I had a computer program that was running this function, running this calculation, and it took some A value and had to run it through tangent A plus 1 over tangent A divided by tangent A. There's a lot of memory and a lot of input that the computer has to go through there, right? Where if I can do the work as a coder to change that expression to cosecant squared A, does that save me room in my computer program? Because now all I have to do is input A one time, right? And I still get the same exact output. Okay? So that's kind of a benefit of being able to do this. Now, what's the byproduct? We learned a lot of, or not maybe learned, but revisited a lot of algebra there that's important for everyday work in college algebra and analyzing functions and that kind of stuff, right? So that's kind of why yesterday our task was to take this function and rewrite it in terms of this one, because there when we get to tangent squared A plus 1 over tangent squared A, after that, it's that game. How can I rewrite tangent squared A plus 1 maybe in terms of secant squared? How can I rewrite tangent squared in terms of sine and cosine? And then how can I rewrite secant squared A over sine squared A divided by cosine squared A in terms of cosecant? And that's kind of the game that we play there. Does that make sense? Now to check to see if we've done this correctly, we should be able to graph these things. Okay, now it's a pain in the butt to type in pretty much any one of the programs that you use as a calculator, but I'm going to go tangent of x plus, was it 1 divided by tangent of x, and then divided that by tangent of x. So it looks like that. And I know that is correct because I know what cosecant squared looks like. Okay? But if I were to graph cosecant squared of x, it gives me the exact same curve, right? So that's proof or validation to us that we have indeed taken something complex, rewritten it, and got something that is exactly the same. We simplified it. Okay? So that's kind of one of the overall tasks in trigonometry is that process. It's called analytical trigonometry. We'll talk about it a lot in Chapter 7 and Chapter 8. Do a lot of those types of questions. And you're going to be of probably two viewpoints. You're either going to love those things. Okay, I like them because I think it's kind of like a game, kind of like a puzzle, or you're going to hate them. Okay, you're going to love them because you're probably good at them. You're going to hate them probably because your algebra skills are lacking, and they create frustration for you. Okay, when I was in school, when I was in your seats, I hated them because I didn't take my algebra. I got A's in it, but I didn't take it serious enough to really understand the purpose of why I was learning that algebra to be successful in that course of trigonometry. So it took me a long time before I could figure out, how do I go about doing these and approaching these so that I'm doing them effectively and learning them with a purpose. Okay, and essentially I had to revisit a lot of my algebra skills and reteach myself much of that stuff so I could be successful in this. Okay, so hopefully we don't have to do that. Hopefully with the examples that we do and the kind of discussions we have with this stuff, it does end up making a whole lot of sense for you. When I was in this class in high school, it was a lot of, I just give you tangent x plus 1 over tangent x with no explanation, no guidance. I say simplify it, and that was really hard. Okay, so I won't teach it that way, but Sammy, you had a question.
When I was following it, I put like the tangent over A at the bottom. I put it looks like this. Like tangent squared A over tangent A, and then couldn't you just put those over too? That's how I did it.
So.
Like instead of how you had tangent over 1, I did that.
Yeah, that's fine, because that's still tangent over 1, right? Mm-hmm. Yep, that's fine. Okay. So that's kind of where a lot of the stuff that we're going to be learning, or that we have learned the last couple of days, and we're going to learn today, use today, kind of show some graphs today, are going to try to lead us into this task. Okay. First thing I want to do is draw or give you insight, I guess, of what we're trying to come up with today. Today, I'm trying to give you, and I think the last class, all we got to was a brief introduction of where that curve comes from. Okay? So what I want to do is I want to set up with you our X and Y axes for this thing, okay? You notice on your Y axis, what's the largest number you're going to need? 1. What's the smallest number you're going to need? -1, okay? Now on the X axis, that thing's going on forever, right? Okay? So this is what we call a periodic function. It's doing the same behavior over and over again, right? Okay? If I look at that number right there where my cursor is, anybody want to take a guess at what that number is? Between 6.2 what? Okay, I'm going to say it's a little bit to the right of that. It's approximately 6.28. What number is approximately 6.28? 2 pi. Okay? So, that, and if we look at this number here would be 0, obviously, right? Okay? This number is 2 pi. So our x-axis, guys, is going to actually be rewritten in terms of the radians off the unit circle. Okay? Now, as we do this, there's a lot of different ways of doing this. I kind of, just to stay consistent with what we did in last class, I'm going to kind of do this with you. So let me get rid of this object. Let me get rid of the axes here. Or at least the numbers on the, I didn't want to do that. I want to get rid of the numbers on the axes. All right, so 1, 2, 3, 4, 5, that would be 6. Let's actually go this way. Let's see where 6 would be there. Okay. All right, so right there would be it's 6. I'm going to say that's just 2 pi for us. It's just going to make things a little bit easier. Okay. So basically, in constructing the x and y axes for this process, is that we still have our integers up there. Does that make sense? On our x-axis, we're just not going to highlight those. It's much like when we do highlight our integers, we usually don't put like 1/2 and 1/3 and 1/4 and 5/4 and 5/7 up on my x-axis, right? Because those are kind of inconvenient a lot of times for the algebra that we're doing when we're graphing things. We like to use our integers, okay? Well, for graphing our trig functions, our integers really aren't all that convenient, okay? Because when I take the sine function and evaluate it at like 2, I don't know what I get back. But when I take my sine function and evaluate it at pi over 6, don't I know I get back 1/2? That kind of makes sense? So I know some certain values on the x-axis that I want to evaluate at. And those places on the x-axis that I want to evaluate at come from the unit circle, and they go from 0 to 2 pi. So the first thing we're going to do, every single time you see one of these, you're going to, and I ask you, I think on a lot of the quizzes I give you this year, I'm going to kind of lay out the x-axis for you. But if you ever get in a situation where you have to do it on your own, I want you to know how to do that. Okay, and it's pretty easy. First thing you do is you find 0, and you find 2 pi, wherever you want those to be. Then I'm going to go halfway. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 2, 3, 4, 5, 6. Halfway, I'm going to put what? Pi. Halfway between 0 and pi, I'm going to put pi over 2. Is that all right? So then halfway between pi and 2 pi would be 3 pi over 2. With a lot of stuff we do, guys, that's what we need. We need those 4 points, essentially 5 points, because we have 0 there as well. But I want to go a little bit further, okay? But those are nice because think about how you graph x squared. You usually use x to be 1, x to be 2, x to be 3, right? Because they gave back, 1 squared would be 1, 2 squared is 4, 3 squared is 9. They give back real nice numbers to graph. Those are going to give back real nice numbers to graph. If I think about sine of pi over 2, it's 1, right? sine of 0 is 0, sine of pi is 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0. So it gives me really nice numbers to graph. Does that make sense? But there are others that we can use. So I want to talk about how we generate those. So, and it's all about just kind of taking these intervals and cutting them up. If I cut this interval up between 0 and pi over 2 and half, what's that marking going to be there? Pi over 4. So now what I do is essentially every block and a half here is going to be a pi over 4, right? So I go block and a half, block and a half. So this would be pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi, 4, 6 pi over 4. Good. All right, and then we get 8 pi over 4, right? So those are good. But now, though, think about, between 0 and pi over 2, if I break that up into thirds, doesn't it give me my 30 degrees, 60 degrees, 90 degrees? Does that make sense? Or my pi over 6, pi over 3 increments, okay? So what's nice, and this didn't work out in the last class because I did it on the whiteboard. This kind of works out real nice here because if I essentially break this distance from 0 to pi over 2 into 3, or into thirds, it's going to be a marking there and a marking there, right? So that's going to be pi over 6, and that's going to be pi over 3. Okay, so I add 30. If I do this in degrees, it would be 30 degrees. There would be 60 degrees. There would be 90 degrees. And then I need 120 degrees, which would be right there. Does that make sense? 120 in radians is 2 pi over 3. Okay, I'm going to add, if I'm in degrees, add 30 degrees of that. Or, yeah, I'm going to add my pi over 6 increments, so this would be 5 pi over 6. And I'm going to keep doing that. So should be over here to get the next one, so that's going to be around 5 pi over 4. That's going to be 7 pi over 6, good. This is going to be 4 pi over 3. Jump 1, it gives me 5 pi over 3. And then this one's going to be 11 pi over 6. And that's kind of how the x-axis is broken down, okay, with the marks around the unit circle. And if you think about the unit circle, that should be kind of mimicked in regards to the spacing. If I'm looking at the unit circle, pi over 4 would be right there, correct? Well, pi over 3 and pi over 6 are only 15 degrees difference, right? So they're jammed closer to pi over 4 than they are to pi over 2 into 0, right? So that's why we're kind of huddled around the black values that I've written up there are huddled around the red ones, right? Okay, they're closer to the red ones than they are the blue ones. Traditionally speaking, though, when we're doing these tomorrow, the next day, we start really developing and understanding how to graph these, we won't be putting in all those pi over 6, pi over 4s, pi over 3s. We'll put pi over 2, pi, 3 pi over 2, and 2 pi. And that should suffice, okay? Now, when we do transformations, when we move these things left and right, up, down, stretch them, that kind of stuff, we might have to incorporate a few of those values, but we usually don't do all of them, okay? So now, what I want to talk about is how we'll just deal with the sine curve today, how this sine curve is developed. So what we'd be looking at, what we'd be looking at for the sine curve is actually the equation y, actually let's do it this way, f of some radian equals sine of that radian. Okay? So I'm just going to put radian because that's my input, right? So that's what we're graphing right now. The output is going to be the y value off of the unit circle. Okay? So when we put the input here, okay, so this input is going to be a radian, so that's the x-coordinate. This is going to be the output. Well, that output, the sine, is always the y value off the unit circle, right? That make sense to everybody? So this would be the y value from unit circle. So every time that we graph this curve right here, that's the sine curve, every point on there has an x value that is some radian around the unit circle, coupled with or paired up with then the y coordinate of the ordered pair off the unit circle for that radian. Okay? And I'll show you, we'll go to this picture here in a little bit and kind of show you the breakdown of how that's generated and all that kind of stuff. But I want to talk about this one a little bit more. So let's just kind of go from memory. If I'm on the unit circle, or if you've got your unit circle in front of you, okay, what we're doing here, let's draw a quick unit circle here. If this point right here is 1, 0, right? How many radians is that point right there? 0, right? Okay, so 0 radians. What is the y value of that point on the unit circle? Which one of these do I choose? 0. So 0, 0 gets plotted on this curve. Okay? Now if I'm at this point right here, which is a radian of pi over 6, that ordered pair, radical 3/2, 1/2, right? So the ordered pair that I'm going to graph down here is my radian, comma, the y value off the unit circle for that radian. So pi over 6, 1/2. Does that make sense? So we'll plot that point right there. Now, pi over 4 would be the next radian, right? So let me see if I can get, let's do this. Let's plot the point pi over 4, comma. Now, what would be the y value for pi over 4 in the unit circle? Radical 2 over 2. So I'm going to write square root radical 2 over 2. So it gives me about that point right there. Now I've messed my placement of my points up a little bit because this is not necessarily, that's right, that was 6, right, not 2 pi. So everything's off a little bit to the left. So let me just kind of do that. Okay, then we use this. Oh, that was bad. Oh, there we go. Is that right? No. There we go. That's where I want it, right? All right, so we won't touch that again. All right, so now we want to go to pi over 3. So pi over 3 is going to have a y value. Pi over 3 is the x-coordinate, but what's the y value of pi over 3 on the unit circle? Radical 3 over 2, right? So radical 3 over 2 is about 0.866. So I'm just going to ballpark that. Let's say it's about right there. Okay? Okay. Now I get to the next point right here, which is a really nice one. That's pi over 2, right? What's the y value for pi over 2? 1. All right? So those points right there, if I connect them with a smooth curve, those points, smooth curve, those points are the points on the sine curve that are generated from the first quadrant, right? Now the points in the second, we'll do this again tomorrow, I don't have time right now, but the points in the second quadrant are those just kind of going in the reverse order, right? Okay, so at 2 pi over 3, I'll be at radical 3 over 2. At 3 pi over 4, I will be at radical 2 over 2. At 5 pi over 6, we'll be back down to 1/2. And at pi, the y value is 0. So now with smooth curve, much better. We get that, right? Okay. Now we can do the same thing throughout here, but 3 pi over 2 is going to have a really nice y value. What's 3 pi over 2's y value? -1. Okay. If I wanted to go 7 pi over 6, that's -1/2. That's a nice y value. 11 pi over 6 is negative 1/2. That's a nice y value. And then 2 pi is at 0, right? Smooth curve. We get what we call one period of our sine curve. All right? So that creation is a radian. Every ordered pair is a radian, comma, then the y value from the unit circle for that radian. What do you think the cosine curve is going to look like? Not the opposite. It's going to be radian, comma, x value off of the unit circle for that radian. And what happens then, sine and cosine, the only thing that changes between those two names is CO, right? That CO stands for complementary. Okay, complementary means they add up to 90, correct? Or I could take one and subtract 90 from the other one, right? Basically what that means is if I were to shift that one there 90 degrees to the left, okay, or pi over 2 units to the left, I get the exact same thing as the cosine. Okay, and we'll talk about that tomorrow. Talk about cofunctions, all that kind of stuff. But when we get to class tomorrow, I want to regenerate the sine function just using 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then we'll generate the cosine, and then we'll talk about how we can manipulate those to change them a little bit.
And we could, as I see you did it for last class, you could assign values on your y-axis.
Yes. So, and that's the thing about doing this. That's why we choose the pi over 2 increments. Like ballparking where radical 2 over 2 and radical 3 over 2 is kind of hard, right? But as long as we on our y-axis, if we keep it consistent, the same every single time, our curve should still be smooth when we're done. No homework. Thank you, too. Tyler. Get you to the end of the night? That work? All right.